Good morning, everyone. My name is Marco Calderon from Deakin University, and I belong to the Sustainability Research Group. Today, I will be talking about the use of pseudo ground truth data for constructing historical land cover maps. As we know, like more than 70% of the ice, of the Earth's ice-free land shows some kind of transformation, but those changes are required for providing food, resource, shelter, and other resources to an increasing population. Nonetheless, a complex array of factors influence these dynamics, and for assessing these dynamics, we require classified spatial data, like land cover maps, and supported by ancillary variables. However, we have a lack of long-term spatial datasets at high resolution, mainly because of technical limitations that can be, I can cite two, the high computational resources needed for handling all this information, and also the lack of historical ground truth data for training and validation. In the case of Australia, that is a country with a highly heterogeneous landscape with 49 ecoregions and more than 400 subregions. Land cover changes are happening at fast pace. The land cover information available for Australia is a 250 meters resolution, the best one, and is based on modest imagery and produced. It is under the name of the Dynamic Land Cover Dataset, produced from 2002 onwards at the early time step. It contains 22 land cover classes, and it's a resource. It's a useful resource for analyzing land cover and land use change dynamics at a coarse resolution. However, it is not well fitted for capturing patterns and trends happening at finer grain. There are other global maps at finer spatial resolution. However, those are only available for a few time snapshots, so we don't have long-term data series at high resolution in Australia. Now, we have cloud-based platforms such as Google Earth Engine that are facilitating the analysis of large spatial datasets. In the case of Google Earth Engine, contains a growing catalog of geospatial information, and it allows the user to pre-process, classify, and post-process the information in an efficient way. The aim of our research is to present an analysis of the historical land cover dynamics from 1985 to 2015 in Australia at high resolution of 30 meters using Landsat imagery. We have selected 6 land cover classes: cropland, forest, grassland. Grassland, in our case, contains shrublands, grassland, pastures, and those. Build-up areas, water, and other areas that are barelands, salt lakes, and those two. And also, our aim is to employ a semi-automated scalable method for reconstructing these historical land cover maps that can be easily escalated and can be applied elsewhere. We follow a three steps process for producing this, for constructing these maps. The first step is the pre-processing of all the raw imagery. We calculated the spectral signature and the ancillary variables for every pixel in Australia at 30-meter resolution. And we calculated, for constructing the main based imagery that was used for the classification. The next step was the construction of the pseudo ground truth data. So for doing this, we used the DLCD map, the Dynamic Land Cover dataset map from Australia at 250 meters resolution, and we extracted the land cover class information of around 150,000 pixels around Australia, following a stratified random sampling design. We also gathered the spectral signature and the ancillary variables information for every pixel. We did that for checking the intra-class variation of these pixels. So we are taking the DLCD map as the reference, so we believe that they are telling the truth. However, some of those pixels are mislabeled due to uncertainties or due to the scale of the resolution of the maps. So we check the intra-class variation of these pixels that we extracted using a PCA We used a PCA, principal component analysis, because it groups pixels together that share similar properties. In this example, the blue points belong to the water class, yellow to cropland, and orange to grassland. So we can see that in this case, these are more similar pixels that are grouped together, and water is in the other side of the ordination plot. So we established different thresholds for every class for dropping the potential mislabeled pixels, those pixels that we believe that might be or have a higher uncertainty of being mislabeled. We established different scores for every class, and we drop all the points with scores higher than those thresholds. So in this case, in this example, we kept only the points inside the circle, and we drop all the rest of the points. We did this for every year and every class, and finally, we retained the invariant pixels. That means pixels that did not suffer any major transformation through time. So at the end, we used just one training and one testing dataset for the whole period. And we kept around 30,000 pixels that were split for training and validation, 70% for training, 30% for the validation process. The final step was the classification itself. We used a random forest classifier. We ran 5 different random models for every year. We did this for checking the discrepancies, for checking the stability of our estimations. We used 5 different subsets of the training data in a random way, using 100 trees and 49 explanatory variables. So the output was having 5 different land cover maps for Australia. This is for let's say, for 1985. We did this. We produced at the end 7 land cover maps from 1985 to 2015 at 5-year time step. So in the case of 1985, we had these 5 different different outputs, and we calculated the mode as the most likely layer, the most likely land cover class for every pixel, and we also calculated the entropy as a way to assess the uncertainty and the confidence of our estimations. Then with the testing data set, we did some accuracy assessments of the standard accuracy assessments. And with the entropy, we are going to use the entropy for doing some post-classification process for some correction after the classification. Our results, we have produced successfully 7 consistent land cover maps for a 30-meter resolution for the whole Australia using Google Earth Engine. And our preliminary results shows that around 9% of the Australia extension have suffered some kind of transformation in our study period. The entropy that we calculated, and the discrepancies among models, shows that overall we have high agreement between our different runs of different models, and the gray areas in the map shows the areas where we have disagreements. That means that different models have different land cover classes for those pixels. So with this, we can do further analysis if we want, but it is, and the main discrepancies that we have calculated are in areas with sparse vegetation, as in this case, are also in areas with bearlands or in the fringe of bearland with salt lakes. So we have some discrepancies along those classes. But in urban and water areas and also in closed forests, we have high stability, like low uncertainty among our predictions. The land cover composition for 2015 in Australia shows that grassland is covering around 70% of Australia, followed by forest with 23%. And we calculated the relative change for each land cover class. So cropland have reduced, our preliminary results show that have reduced around 20% in whole Australia, and built-up areas have increased around 16% for whole Australia. In the case of Victoria, I stayed in Australia, the land cover composition is more homogeneous, with forest covering 43%, followed by grassland and cropland with around 30%. And the relative change for Victoria shows that croplands have reduced in around 4% of the original areas, and built-up areas, urban areas, have increased in 36%. With this, we can also assess, we can visually and quantitatively assess land cover transitions. This slide is showing the 1985 land cover composition overlaid in the 2015 extension of Melbourne City. So that means we can assess that, and we can see that Melbourne has grown into the northwest area, into former grassland, mainly in former grasslands, and also in some croplands. The accuracy of our estimates are between 92% and 94% throughout the time. And if we compare this with our reference map, the DLCD, that one has 82% of accuracy. Our kappa values are around 0.9, and the producer accuracy for every class is almost is pretty high. It's pretty good in every class. Some final remarks is like our method can be escalated. We have used this method, and is easily to be applied in other areas. Producing every map, it takes around 2 to 3 days for exporting for Australia. So smaller countries, it will take less time. And we will use these maps for building some land use simulation model using machine learning approaches for predicting future land change in Australia. Thank you. Yeah, these are some preliminary results, and you are right. Those accuracies were just for every time snapshot. We will calculate different accuracy measurements for assessing change. We have only done some preliminary assessments of potential change, but we have to calculate in a deep way to have some more robust results.
Maybe I can piggyback on that question and ask, were the maps that you produced on a yearly basis also used as prior information for the other years, or were they produced completely independently?
For example, for every year we use the information of 2 years before and 2 years after of every year. So we calculated the median of the spectral signature of the points for having the raw image that we use for the classification. So let's say for producing the map of 2000, we use the information from 1998 to 2002. We remove the clouds, the pixels with clouds, and other bad pixels, let's say, for having a good image, a good base image.
But you didn't use the other maps that you produced, say, for 1985?
No.
For 1990?
No, we haven't used that.
Okay. There was another question. Casey.
Thanks for that, Rodrigo. My question is about the savannas of Australia, which were missing from the classification. It was forest or grassland. And savannas are a real pain.
Yeah.
Classifications, because they don't fit neatly into either class. So how did you define the savannas? And are they changing fast in Australia? That's really what I'm interested in.
Well, yeah, we use our reference map doesn't have the savanna class, so it has different shrublands, tall shrublands, small shrublands. So we group those classes together. So the savannas are mixed into our grassland category. So we did this because we don't have enough information for, as you say, it is a pain to deal with those. So we cheat a little bit for having some broad classes that we can later, with more information, we can include more classes and make the maps more accurate and more detailed. Thanks.
Yeah, I think it's really an interesting case because it's a national case, so I guess there are more questions in the room. But for the sake of time, I would say we spare that for the end, and I hope we have 10 to 15 minutes left, and then we have a broader discussion with all the presenters later on. So I would like to introduce the second speaker of today, who's Veronique De Sy, and we will hear. Thank you. Of course, sorry for that. We will hear about innovating land monitoring in support of climate change mitigation and sustainable land use options. It's work presented by University of Wageningen, and I'm looking forward to your presentation.
Thank you. Okay, thanks very much. So I want to talk a little bit about land monitoring, specifically in support of some of these sustainable land use strategies. And I'm drawing upon work done at our chair group, the Laboratory of Geoinformation and Remote Sensing, but also from other chair groups in Wageningen, for example, the one you also heard about this morning about the Yield Gap Atlas, the Plant Production System chair group, but also on work done by C4 on REDD+, for example. So within this climate change mitigation and sustainable development and land use, there are several agreements and goals on the international level. So you have, of course, a Paris Agreement where the land use sector, some countries propose targets in the land use sector in their nationally determined contributions, their NDCs, and these are specifically also this land use sector is still very important in a lot of the developing countries, because here you have still quite relatively a lot of emissions from your land use or your land use change. Also, of course, REDD+ targets tropical forest countries, and REDD+ is more about reducing emissions from deforestation and forest degradation. And then, of course, the Sustainable Development Goals, where, again, in these regions you have, for example, improving food security is still quite important and has a big link to the land use sector. And often these countries, they do have high mitigation potentials, but the monitoring capacities are low, and they have a need for spatial information on agriculture, forestry, and land use or land use change to improve their greenhouse gas inventories. Also, there will be a regular stocktake for the Paris Agreement where this information is needed, but specifically also to support their national policies, because in the end, monitoring is not the goal. It's a way of sort of supporting also the policy, because of what you want to do is get at policy change and seeing also changes on the ground. So today I want to focus more on this sort of land monitoring in support of national policies. And because monitoring capacities are so low, it's interesting to see whether a lot of these global products coming out and also new methods coming out, specifically also spatial information, how that can address some of these monitoring challenges. And I will focus on these three policy stages. So when it comes to policy design and planning, I want to focus on a study done on direct drivers of deforestation, and another one that deals more with this climate change versus food security trade-offs. So agriculture is a main direct driver of deforestation. This was a study done across the tropics. It used a systematic sampling design. So these samples are 10 by 10 kilometer squares, about 100 kilometers apart. And within these samples, I looked at when there is deforestation, what is the follow-up land use as a proxy for the direct driver of deforestation. So you see all these dots, these are the deforestation. The bigger the dot, the more deforestation. And the colors give sort of to which land use the forest was converted. And of course, you see here the arc of deforestation. It's mainly pasture. You have some brown hotspots, which are large-scale cropland conversions. Africa, you see much more domination still of small-scale crop systems. While in Asia, specifically Indonesia and Malaysia, you see tree crops. This is mainly palm oil. And here, more in the continental Asian countries, you see also still a bit more small-scale crop. And of course, the fact that agriculture is a main driver of deforestation and also where it is occurring, for which reason, is not that new, but there's not a lot of studies that really quantify this. Of course, we also have recently the Curtis published a data set quite similar to this, but it's wall-to-wall, and it's also based annual data, which is also quite nice to see, but it has a bit less thematic detail as well. And so why is it important to also look at sort of this quantification and more the spatial distribution of drivers? One, you get a better sense of sort of, if you look at deforestation, so what percentage is caused by which direct driver. So this is just aggregated at the continental level, but you could also do the same for the national level. And I think this opens also some ways to link your deforestation with more underlying drivers through these very specific land use transitions. And you can also start combining it with all kinds of other spatial information. For example, we combined this data with global biomass map. And we looked at, if you look at the mean carbon stock estimates of all the forests in these continents, and you can compare that with the converted forest, you see here, and this is quite obvious in Latin America, that these converted forests have a much lower carbon stock. But you also see, if you look at forests specifically converted to pasture, and for example, small-scale cropland, that small-scale cropland occurs much more in these higher carbon forests. And of course, it's not so easy as to say, well, then we'll stop expanding our agricultural area. And so I want to highlight also this with sort of this food security versus climate change mitigation. And this builds on the same data that was shown in Grassini with Professor Grassini this morning with the yield gap data, and looking for a few African countries. For 4 scenarios, if you want to reach full self-sufficiency in 2050, what does that mean for your greenhouse gas emission? And you have to choose between sort of intensifying or expanding your cereal cropping to actually reach that self-sufficiency. And it looks at 4 scenarios where in scenario 1, it's actual yields. Scenario 2, you extrapolate the yield trend. And then at 3 and 4, you look at 50 or 80% of your potential yield. And because I don't have much time, let's look at the total of these 10 countries. And you see, and the gray one is the fertilizer use, and the dotted line is the greenhouse gas emissions in 2015. And you see in all scenarios, basically, that you won't be able to if you want to reach self-sufficiency, that you will always have more greenhouse gas emissions. And if you're not able to improve your yields, you will have a lot of greenhouse gas emissions, of course, from your land use change. And not so much. The fertilizer is sort of a lot smaller here than the emissions you get from your land use change. So this can be also a way, and you would want to do this also more spatially explicit, to get at these trade-offs. And it kind of shows that there might not be a win-win situation here. Since I don't have much time, I will skip this. This has just to do with radar tree cover loss alerts for your which might help with your policy enforcement. But I want to go more to policy performance and evaluation. So, and this is more specifically for REDD+. At one point you might want to see, so how did my REDD+ intervention performed, for example, on the project level? And often this is still quite difficult, and we wanted to look in, if you use, for example, a global forest cover product from Hansen, or you use an open source algorithm for change detection, and how do these perform, looking at sort of prediction of forest change. And we did this across 5 initiatives in 4 countries, and we didn't really see one of these products popping out. It really depends on the site, and it's difficult to predict which one performs best. There's some complementary. You can actually combine the 2 products, and that might increase your accuracies somehow. But especially interesting is that you get sometimes very different deforestation trends, because you're interested in sort of the percentage change in your before and after period. And here you see the trend for Hansen, and here for BFAST. And you see that these can change quite a lot, so it really matters which products you use, whether you can say whether your interventions worked or not. And of course, we also did an accuracy assessment, also with a stratified random sampling approach. And then again, you get very different trends sometimes. We also did a trend on, we also used confidence intervals to have a better idea about the trend uncertainty. So if you then go to REDD+ performance and you look at, for example, the annual deforestation in your before period and in your after period, well, you see some trends, but if you include your confidence intervals, these often overlap. So you're actually not that certain about your trend. So you, in these sort of red squares, there's overlap between the confidence intervals. So you cannot really say that much about the actual performance. And this is really problematic because you, also this is the basis of result-based payments, for example. In Indonesia, there was a clear trend in both confidence intervals. And in Peru, it really matters whether you use a 50% or a 95% interval. So this was just to show you some ways of, so how you can use a lot of the data and methods that is around to get at information for policy change. But of course, just having more information and better information is often not enough to get to your policy change. And this is a chapter I wrote together with some colleagues from C4 in their new REDD+ book on sort of, you know, what are actually the obstacles in information and achieving policy change. And this takes the case for data on drivers, but I think the messages are sort of more wider applicable where, yes, new information really offers new opportunities, but it also comes with implication and risks. So I have to stop, but my main message here there's also a very political dimension in generating information and building monitoring system for specific national policies. So I will stop here. Thank you.
Yeah, thanks a lot, Nikki, for bridging between remote sensing on the one hand and policy needs on the other hand. Questions, please. To both sides, the remote sensing side or the policy.
Quick question on the last part of the analysis where you were looking at Matt's GFC product and PFAS. Did you also look at, you had trend differences, did you also look at total area estimates of disturbance or loss?
Yes, we also did actual area estimates indeed. Yeah, and so you can see that here you see so the bars are for the reference data and the little symbols are the area, well, this is still annual deforestation, but these are built on area estimates indeed. So, but you see that there's very different trends sometimes. Yeah.
We were finding the same thing using Matt's product and PFAS and
Yeah.
Yeah.
Yeah. And I think one of the main messages is here that your accuracy assessment is very important, and especially your sampling strategy as well, because these bars, you can probably, with maybe more samples, you can sort of narrow them down a bit, which then you might actually be able to show some performance. So either which products you use, I think the accuracy assessment and the sampling is actually quite important.
And just a follow-up question on Peru, there's clearly an anomaly between the GFC and the two other products that you're using.
Yeah.
Can you hypothesize why you're seeing growth or?
I'm not sure specifically about Peru. What you sometimes saw is that if the after period was not so long, that sometimes Hansen needs a few more years to actually be able to predict better, sort of sometimes these things. But we couldn't really always find clear reasons why one would perform very different from the other, which is a bit scary because then you also don't know when to apply which product. Yeah.
Well, you don't have to collect any more data by just, with this slide it shows you can just make more narrow confidence intervals by decreasing your confidence level. Can you tell us, I mean, I haven't seen a 50% confidence interval before. Can you tell us about the history of how that got?
Well, it has to do also with this conservative principle. You have this paper by Grassi, I think, and it's about, for RED+, how conservative do you want to be when you talk about your difference and your trend analysis. And I think he uses actually a 50% confidence interval. So no, sorry, maybe that was not your question.
It was. I mean, and so is it one person who said, well, let's try 50%? I just don't know the history of how that got into the culture.
Oh, yeah, so that is quite an arbitrary number, yeah, of course, yeah.
As is 95.
But I think it's, yeah, as is 95, but this is also something that at one point has, you maybe also higher up when in the RED+ sort of ecosystem that has to be decided what is acceptable and what not, I think. So when can you actually show performance? And it's not so easy, and often this step is even forgotten in a lot of these RED+ projects because they're often more about livelihoods and these kind of things, and then at the end they think, oh, but we have to show carbon performance, and not a lot of studies are done that actually deal with this aspect of RED+, while it's one of the main goals, which is, yeah. It's one of, also now moving into this result-based phase, it's one of the challenges, actually.
Just very shortly on the Peru case, because it strikes me as well, and what we probably also see here is that those areas where we are, for example, in the Andes, are among the most critical ones to map overall. I mean, savanna is a pain, as you said rightly, but the mountainous areas where data density is really poor is another pain as well. So one thing we can take home already now after 3 hours in a conference, because it's also the plenum, is uncertainties are among the most important things on the agenda to trace back. So that's a really important.
And the Tanzania drier forests, also very complicated.
Talking about Tanzania, actually, got me thinking, so you see an increasing trend in forest cover. Did I interpret that right?
But you're not certain about that trend, but you can sort of,
But the whole region is getting more woody. Like across the southern African savannas and woodlands, it's getting more woody, not because, well, humans may be indirectly driving it, but we don't know that. But the whole area is getting more woody anyway. So how much of this is actually, like, if this was carbon accounting from emissions, you would say how much of this is due to like direct human action and how much of it are we going to ignore because it's the natural carbon cycle? Does the same apply here?
well,
How much can you attribute to the red policy and how much is just the background regulation?
that is now the next step where we're getting at, because if you want to do a policy evaluation, you want to know which interventions worked and which not, which were due to the intervention. And within the same study, and this is part of the global comparative study on RED+ from C4, they also did household surveys in these RED+ initiatives. So these are very specific projects, and also they did another paper, this is one of our PhD students, did a Baki approach, so not only a before-after, but also control intervention. So you would see that in some cases your deforestation would increase, but it would increase less than the control. So, but then you would need to really get into even more other methods, and trying to link it then to household data that's also very complicated. So we are really not there yet. This is just one of the steps, I would say. You're right, you would need to do a lot more to be able to attribute it to RED+. Yeah.
Okay. Thanks very much for that.
Thank you.
I allow myself to switch order here to streamline it a bit, and we have as the next talk, flash talk by Doktor from the Environmental Research Center at Leipzig, who will talk about introducing dynamic composite periods for pixel-based crop type mapping using Sentinel-2 imagery. So, the floor is yours then.
That's right. Yeah, hello everyone. So mapping land use based on satellite imagery is composed of two main steps. First, data compositing in order to account for cloud coverage and to ensure a spectrally consistent trajectory. And second, on the classification, the subsequent itself. I will focus on the former one. So standard approaches employ a regularly compositing period, as you can see here, 2 weeks, for example. And the weighting of these periods is usually related to scoring functions which relate to the main photosynthetic peak of the vegetation. However, if you classify land use or crop types, these might actually substantially deviate from those mean peak. And even if you want to discriminate those two, there could be also other time periods important which are not in this main period contained. And even if you could identify an ideal observation point here, for example, how would this look like in a satellite imagery? Cloudy perhaps, maybe black-filled as well. And where would be your training data in that satellite imagery? That's why we came up with an alternative approach where the composite periods are not defined regularly but flexible based on cloud coverage and training data only, and the weighting is actually then left to the classifier. And we also do a regionalized classification in order to account for this spatially varying training data availability and cloud coverage. Here we divided Germany into 6 areas: the northwest and east lowlands, the uplands in the west, southwest and east, and the alpine forelands. And that's what we get. These are the flexible periods, composite periods now. And you can see there are not equally spaced over time, the black boxes here. There are big differences, for example, in the number of identified composites between southwest uplands and west uplands. 6 here for the southwest uplands and 14 in the west uplands. And also the time where you have observations or composite period changes between each of them. And that's what we get. We could identify 19 crop types with an overall accuracy of 87% across Germany. Some examples here. Main crop types over 90%. And as we heard, uncertainty is important. We also can attribute a classification error for each pixel, which is of course related to data availability. You can see non-overlap of the sentinel stripes, which transposes into the model. And that's then also not only regionalizable, but also scalable and transferable to other regions to hopefully map the ecosystems of the future globally in the future. Thank you.
Thanks a lot. Time for one question here. If not, I have a question actually.
Yes.
Because I think it is a great example how to adapt classifiers to the needs of the region. On the other hand, how do you adapt in areas where data is still scarce? So for example, where cloudiness is high. We had that example of Peru just in the previous talk, and if you want to unfold that at a global scale, how do you guarantee that if the classifier chooses the temporal window, if cloudiness is prevailing, how do you deal with that?
Well, the classifier only picks spots where you have training data there at times where there are no clouds. And that you can see here. So for example, in the southwest uplands, we had much less training data available than in the other areas, and consequently, you have also less composite periods here identified. The interesting thing is that even though the numbers are quite different, the performance was quite similar, and we actually think that we are running kind of to a classifier problem in terms of overfitting. So it's not actually the number which is limiting the outcome, but it's the overfitting if you put too much data into the classifier.
Okay, that's an interesting one. Thank you very much. So it's Céline Lamarche who will go on a full talk. It's a group of Pierre Defournier in Louvain-la-Neuve, and it's about annual global land cover maps from the 1990s to 2016 for climate modeling.
Is it okay like this? Okay. So thank you, Patrick. So my name is Céline Lamarche, and I'm working in the UC Louvain Geomatics Lab in Belgium, and I will present the land cover component of the Climate Change Initiative, which is now part of the C3S Copernicus service. So we have been working on land cover, but actually we are part of a bigger program, so the Climate Change Initiative from ESA. So among the 50 essential climate variables, ESA has decided to monitor 25 of them, and land cover is part of the lot. So in terms of terrestrial ECVs, in the first phase we were 5 terrestrial ECVs, so land cover, fire, ice sheets, glacier, and soil moisture. And of course, there have been a lot of interactions between us. So we haven't started within the Climate Change Initiative. Actually, we started some time ago with the Globe Cover experiences. When we released the Globe Cover 2005 and 2009, where the outcome was really to build an automated chain using Mary's data and providing a land cover map with 22 land cover classes. Then there has been a release of Globe Cover 2009, and there we realized that actually we couldn't achieve any consistency between the two dates. And then we started the CCI land cover project, where we provided 3 5-year epochs, ensuring there the consistency, because it was the main user requirement from our climate modelers. And between the 3 maps, we had only forest change. And now the last output of the CCI land cover was a set of maps, annual land cover maps from 1992 to 2015, including 13 types of change. And now, since 2018, we have entered an operational service, so the Copernicus Climate Change, and we are now producing in an operational manner additional maps from 2016 to 2019. And so the first start, of the CCI project was really to revisit the land cover concept in order to achieve this consistency between the years. So we had redefined the definition of land cover by really characterizing the 3 components completely separately. So the stable part of the land cover, the seasonality, and the land cover change. And this concept was translated into a processing change, which decoupled the land cover, the seasonality, and the change. And so these are the outputs of the CCI, so really the land cover maps, the stable part. We have 3 seasonalities, so these are the average behavior of the snow, the greenness through the NDVI, and the burnt area that are provided for each pixel. And for each pixel, you can have the occurrence probability for snow, burnt area, and an average behavior for vegetation greenness. And in addition, the land cover change is mapped completely separately. So in terms of processing chain, we have those components that are really visible separately. So the baseline, which is the stable part of the land cover, uses the full archive of Mary's at 300 meters to have really some stable information on the land cover. Then we have the full archive of AVHR, spot VGT, and ProBavi that are classified on a yearly basis. And we analyze this series of classification to have an information of change that is then updated, that is used to update and backdate the baseline. And this is how we ensure the consistency between the years. And of course, as we are part of a big program, we are using directly some information from other ECVs directly in our products. So these are the series of inputs that we are using for the baseline, so the stable part of the land cover. So this is Mary's data. And then for the annual land cover database, it's more spot VGT, Mary's, and ProBavi. So if we have a closer look on the change detection, then here are the classified data from AVHR, spot VGT, and ProBavi. So each year, this is a separate classification. And then we are extracting for each pixels the series of the trajectories of the classes that we are mapping at 1 kilometer. And then we have defined a set of rules that scan the time series and allow for the detection of changes. And of course, these are some uncertainties between the different classifications, but this is taken into account by first detecting potential change and then confirming it over time. So the change is detected at 1 kilometer because the input data is at this special resolution, but then it's delineated further as a second step to the 300 meters using back the ProbaV data. And several changes are allowed per pixel. So this is an illustration of the drying up of the Toshka lakes in Egypt, just to show that this is quite consistent in terms of spatial delineation of change and also in the temporal way. I have some illustration for the recent years. So between 2015 here and 2017, there had been a dam constructed here and a cropland expansion in Angola. And actually we are able to detect it here. This is a closer look just to show that this corresponds to the reality, actually. So these are the kind of examples that we can have on an annual basis. And so the maps are validated using a global stratified random sampling that had been built earlier in the first phases of the CC Island cover. And for the moment, we have assessed 2016, and it's actually 71% of accuracy at the global scale. But there was a question about the change accuracy assessment, and because this sampling was built before, actually we only have 6% of the sampling units falling on change. And so the next step of our work will be really to redefine a sampling dedicated to the change assessment. And we have all this data available online on a viewer that is interactive, so you can right-click to have the seasonality per pixel, and on the left click you can have the land cover legend, and it's also the place where you can download the data. In parallel to this, we also have worked with Sentinel-2 at higher spatial resolution. So the first experiment was to derive a continental map, I would say prototype, for Africa using Sentinel-2 for 2016 at 20 meters. And this is done at a legend of 10 classes. Then, as a second exercise, we did a regional map at 10 meters, this time using the full archive between 2016 and 2018, this time at 10 meters, but still with the 10 classes. And this was really an exercise to show that it was possible to process a continent in a timely manner. And this was really to make use of the Sentinel-2 time series as a full, because previously with the CCI land cover map at 300 meters, we were working with seasonal composites, and this time we wanted to try using the full time series of Sentinel-2. Sorry, and so I want to thank you, and just to show you an example of the spatio-temporal consistency that we can achieve here for the deforestation patterns that are captured in Paraguay from 1992 to 2017.
Thank you very much, Céline. Questions to Céline on their products?
Well, you say you're now realizing it's important to measure the accuracy of change, so you're designing your sample to do that. But then
For sure, but by the way we have built the change detection algorithm, we know already that there are some limitations, for sure, because we only map drastic change that is confirmed over several periods of time. So this for sure we know that. It's not that we did not care about change accuracy before, it's just that it was a question more programmatic that we have built this validation database. And now by refocusing on the change area, mainly I would say that the commission errors will be more easy to capture than the omission, for sure. And then we will be able to better address the type of change that, what you said, the maximization of the change detection algorithm. But yeah, this is how it had been built before. So the transition changes are not captured, for example, different types of forest, I mean, passing from coniferous to a broadleaf is not captured for the moment. Irrigation is not captured. So this we know. This is part of the limitation that are reported in the product user guide, for example. Yeah.
Further questions? You rightly mentioned the limitations already, but even that you are now building up a more sophisticated validation system, I think you have a good knowledge already about the shortcomings that will turn up in that validation. So maybe you can elucidate us a bit on which are the most critical classes that you see if you go for CCI global products at kilometer scale. Where are the limitations that we need to take into account when working with that kind of data?
The limitation, so as I said, that there are some types of changes that we don't capture, because when we built the change detection algorithm, we have gathered the 2012 CCS classes to the IPCC classes, and change between only the big groups of IPCC classes are captured. There is also a question about before 2004, we did not have any 300 meters information, so the change is detected really at 1 kilometer. And from 2004 until the current days, we have been able to further delineate the change with the 300 meter information. And so there is sometimes a lag also. If you have a change within a pixel of 300 meters, we need some, test to be changed to a certain extent before the algorithm detects it. So there is a kind of lag in time between the detection of the change. I would say that as you mentioned, according to the different cloud coverage, we know that we need more time, for example, in Amazonia to capture the change than because of the cloud coverage. So I could go on with limitations, but I will stop here because somehow, this product has the advantage of having some classifications. So it's 13 types of change between 22 land cover classes. So for sure we have limitations, but we have also a thematic richness that is, in my opinion, valuable. So.
I have a question to the room, basically. Who's using that kind of data at the moment? Okay, so it would be really interesting to have a match between your experiences and your really challenging work that you do on a daily basis, because I think that feedback is what is needed to further improve such data sets. And it's made for CCI, so it's not made for the land systems community, let's say, but still, as we are having you here, I think it's a great opportunity to match up the needs of that community, which are slightly different in terms of what the processes are that people are interested in most of the time. So let's take that opportunity, maybe
sure.
Also in the discussion afterwards, and
I will remain here.
Yeah, very good. So I would like to hand over for another flash talk of Steffen Ehrmann. He's from the German Center for Integrated Biodiversity Research, the IDIF, as it is for short. And it's on mapping global land use patterns and recent historical changes. Please.
Hello, I'm Steffen Ehrmann, and I want to tell you about, what is that? Okay, no speaker notes. And I want to tell you about, I want to introduce the LuckyNet project and talk about our recent efforts to map global land use patterns and recent historical changes. LuckyNet stands for Land Use Change Knowledge Integration Network, and we have a couple of founding members. You may know some of them. Basically what we have in common is that we believe in an open science, and we want to build in this open science framework data that are available for everybody. So based on the efforts of some of our members, we are basically building gridded model data products of the crop distribution, forest management types, and livestock densities. Those are supposed to be time series ranging from 1992 to today. Since we model them all together in one framework, they're going to be internally consistent, and we assess uncertainties at pixel levels. We put great effort into collecting national and subnational land use census data, basically to avoid garbage in, garbage out problems. And we are also about to collect in situ records of land use. And together we combine them with various remote sensing derived products like ESA CCI, for example, or CHELSA, or also socioeconomic data sets, for example, about the travel time to the nearest market. We are aware that there are different demands for those data sets and that no single data set or no single data product can provide all of them at the same time. So you might, for example, be interested in consistency with national numbers at the global scale for IPCC or IPBES assessments, or you might need a possibly highest local accuracy for resource management, or you might want to do causal research and thus need data set that avoids circular reasoning. This can be, for example, achieved by having various different resolutions that optimize for those purposes, but all of them will have in common that we document their provenance and their quality. So the analytical pipeline will be open, reproducible, and transparent. And it's going to be modular and automated so that we could theoretically, in a future version, take out one module and replace it by another one, for example, by an improved model. These are some very tentative results that we came up so far. And with that, I basically want to thank a couple of people who helped us kick off the project, for example, by the generous possibility to access the databases, and all the other founding members for LuckyNet. If you want to get in contact, here are some details.
Thank you, Steffen. Direct question to Steffen on their plans?
Yeah, this is maybe more general, these things, but all these products at 300, 500 resolutions go back. This is going to ignore probably the vast majority of smallholder agriculture, so basically everything out in Africa, outside of South Africa and Egypt. And isn't that probably the most important area to be looking at crop changes and management practice changes? So I just wonder, are we cutting out big areas by how we approach these things?
I guess, and I think this is one of the aspects why we have a project which we can basically in the future update when there are better data products coming available that would have a final resolution, for example, to assess those things.
So, better data. This is the core sentence here. Looking forward to that myself. And with that, we are switching the agenda to the very last flash chart that is by Ignacio Gaspari. And Ignacio joins us from the University of Tucumán in Argentina. And he will have a flash talk on mapping silage bags, the missing link between agriculture and livestock.
Let's see. Okay, so yeah, just have to try. Maybe in this one. Yeah, it's a bit problematic because there is the HDMI. That's fine. We'll do like that. Sorry, I come later. this one? Or
Yes.
okay. No, I can take it.
Thank you.
Oh, already.
2 minutes later. 1 minute for the
Your time's
sorry.
over.
Yes. Sorry. It's,
Okay, so
it's
yeah.
fair. It's okay.
Okay.
Okay, just to talk a little bit about why we decide to map in the silo bags. Silo bags is a technique to store the grain. Very used a lot in South America, especially in Argentina. More than half of the production of grain in Argentina is stored in silo bag, waiting to be moving to the harbor, or is stored to supply and feed the cows in the pasture. So what we tried to do was to identify where the silo bags are and the size of these through the time. So we think it's important to get more information about the system and intensity of the use, especially in the cattle ranching systems. And traditionally, cattle ranching and cropland is looking like different things or drivers in land use change. But in Argentina, we understand that there are a lot of connection between the two activities, and sometimes work like only one system with a lot of fluxes in capitals and products. And silo bags is one of these, is the physical representation of one of these fluxes. So they look like that here. In the remote sensing, look like this. It's very easy to see in the very high resolution image. But the point is how to identify the silo bags in a large area without people screening all the time the high resolution image. And we use a method using Sentinel-2, spatial resolution 10 meters. And at the beginning we tried to perform a classification, but finally we decided to use a spectral mixing method to have a percentage of plastic in each pixel. And doing this we have a better precision in terms of how many square meters are covered with the plastic bags in each place. So using this method we can prepare some times curves about the area of silo bags. The silo bags have a standard, so also you can estimate the volume of grain storage in each place and through the time. There are validation with very high resolution image of Google, but it's not easy to get all the information to have. There are only 2 points. Oh. The point is there are some problems. Silo bags are in many places, so the mean of the silo bag is different. Here is, for example, to complement the fixed storage capacity in a very important logistic center in northern Argentina. But also we have some problems of change. Problems with false positive. The silo bags plastic is used, for example, in urban areas for local markets. And also we have some problems with silo bags. We have metal roofs are confusing. But at the moment what we start to look is more what happened with the silo bags in a context of pasture land use, and how is the dynamic of the silo bag through time to understand how the agriculture sustain the cattle ranching especially during the dry periods. That's all.